Hi, this is Geraint. Back in November, I presented a talk at ADC about pitch shifting and time stretching, but I was getting a bit pressured for time, so I had to cut a section out. It was going to be a crash course in Fourier and FFT stuff for people who'd never heard of it before, or didn't really understand what it was about. If you do know what that's about, feel free to not watch this video, or just try not to grimace too much as I skate over some of the finer details. Okay, here we go. For any waveform, there is some combination of sine waves and cosine waves at different frequencies, which, when we add them back up together, we get the original waveform again. This is a pretty cool property. Any waveform can be represented as the sum of sine and cosine waves at different frequencies. So you could take your waveform and get a set of coefficients, one for cosine and sine, for each frequency. The Fourier transform is the mathematical process which takes this waveform and gives you these coefficients, which we refer to as a spectrum, and there's an inverse transform which takes these coefficients and essentially multiplies them by the sine and cosine waves to get back a waveform again. Now, I've presented this as a pair of coefficients for cosine and sine, but often we'll deal with these as a complex number, so these will be the real and imaginary parts. And the advantage of this is we can reason about things like the magnitude or the energy at a particular frequency, separate from the phase, which is it a cosine or sine, because they're kind of the same but delayed, or whether they're positive or negative, So this is pretty cool in an abstract sense, but what can we do with it? Well, let's say that I choose some threshold frequency, and for every frequency above that, I set all the coefficients to 0. Then I use the inverse Fourier transform to sum up the same sines and cosines that we had, but only below the limit, and we get a different waveform as the result. This waveform is missing the high frequencies which are required to make sharp corners or sudden jumps, so it'll be smoother, and it will in fact be low-passed. This is a low-pass implemented in the frequency domain. Well, that's all well and good, and very mathematical, but this waveform is infinitely long and infinitely detailed. And the spectrum it gives us, these coefficients, are also infinite. So to do practical computation, we need something called the FFT, which is the fast Fourier transform. What this does is it takes a finite length sampled signal and gives us a finite length sampled spectrum. So the sampled signal is an array of waveform values, and the spectrum is an array of complex numbers, which are these multiplying coefficients. And the frequencies it gives us are all multiples of the wavelength of the signal that we give it, the time domain waveform. So index 1 in our spectrum corresponds to the cosine and sine oscillations, which go round once across the whole length of whatever signal we give it, and so on for index 2 and 3. There is a problem though. If we took this waveform and repeated it, then we'd get these discontinuities because the start and end of our waveform wouldn't match up. But we're reconstructing this waveform by summing up these cosine and sine waves, which are smooth. Now, this doesn't stop the FFT getting a good result, but it means that it spends a lot of information reconstructing this discontinuity from these component waveforms which don't have a discontinuity in them. This ends up cluttering our spectral result a little bit. So what we do is, before we hand our waveform to the FFT, we fade it at the start and end. We taper it so that the beginning and end match up better, and this gives us a cleaner spectrum. There's some maths about what's a good shape for this tapering, or windowing, and you soon run into some, I think, quite cool things like the convolution theorem, linking what happens when you multiply in time or convolve, and what that looks like in the time or frequency domain. But basically, what you need to know for the rest of the presentation is the FFT takes this sampled array of waveform data and gives you these multiplying coefficients for sine and cosine at different frequencies as a complex number in your spectrum. Alright, hopefully that's enough to understand the rest of the presentation. But if you have any questions, do get in touch.